Recording. And I want to start with, wait a second. Here. All right. So last week we did a lot of things. I'm not, for the interest of time, I'm not going to review the logic and PDDL. I'm just going to focus on this thing here. We started talking about the market decision processes. And so the question for you is, what are we trying to get out of this discussion? What is really the problem that we're trying to solve? Anyone? What was the problem? We are facing what? We are facing a planning problem. So it's a planning problem. But this time, the planning problem involves interaction with the environment, right? The agent and the environment stay as blocks the same way as we always has been, right? But there is some signal now that the environment is sending to us that is called reward. The reward. Okay. So that signal, as you can see, this is the interaction, agent, environment, and so on, is sort of represented here with a capital R, right? All these kind of letters are random variables. The capital R letters are random variables. So the environment is a stochastic environment. This means that, what is the meaning of stochastic environment? What is the, yes?
It's randomness in the environment.
Yes, stochastic is randomness. But what does it mean? It means that there is a state transition model like what we had seen where we had the state transition model before. Hidden Markov models, in the hidden Markov models, okay, where I was intending to go forward and I ended up sideways. Again, remember the robot and the carpet. Slippage of the wheels of the robot. Okay, so there is a S prime state. S prime stands for next state. Next stage. Okay. Another source of randomness in this block. Where do you see another source of randomness? Is there another source of? There is a source of randomness because the agent, right, may execute
Actions.
Random actions. You know, I don't have any goal specifically. Yes, I have a goal to exit the room, but you know what? There is a lot of fog around me, right? So I cannot really see the door, and I will go around here trying to find the door. Okay. So I will execute some kind of what we called policy. I will execute some form of a policy. What is the definition of a policy? Okay, are you reviewing the previous lecture? Because this is really the key lecture, the definitions. If we go now to this lecture without really understanding the definitions, then I will tell you at 8 p.m., you will tell me that's enough. Let's get out of here. Okay, so what is the definition of a policy?
Mapping from state to action.
Mapping from state to action. What does it mean? It means that a policy is in general a discrete, let's say, if my action space is discrete, probability distribution. Okay, so I can go forward, backward, left, and right with equal probability. This means I have a probability distribution with how many actions? 4 actions. Each one is probable with probability of 1/4. Okay. Very straightforward stuff. Just think about examples. Okay. The key to understanding is just think of the simplest possible case. So my job, what is really, still we haven't finished with the problem. Okay, we are facing a stochastic environment. We are receiving a signal called a reward, and our job is to deliver what? The pi, the policy we call the letter pi star. The optimal policy, which means for every state that we are in, right, we may need to determine an arrow. Go left, go north, go east, whatever. in the simple discrete world that we have, assuming at this moment in time. So we call this the privileged discovery experience. And we actually discussed a little bit about this. And we discussed and defined this, if you like, an MDP, a problem where someone is providing a transition model. We are given a transition model. We know the probability distribution, in other words, of we know this. We know this. We know the MDP dynamics. What is the MDP dynamics is giving us? Definitely, it captures probabilistic dependency, which we represented always with a probabilistic graphical model, a BGM, whose nodes designate random variables and edges, directed edges, tell us what? Tell us some story about the probabilistic dependencies that we have. So the moment we execute an action, we are immediately transitioning to the next state, right? And get a reward from the environment. And this dependent probability distribution is this guy over here, which it has a name called MDP dynamics. It is the probability of the next state and the reward given state and action. In the hidden Markov model, right, we also had something like this. We had an S prime given S comma A. We also had a measurement model, if you remember. So we are familiar with this type of probability distributions. This is not the first time we are coming across something like that. Okay. So we said, okay, fine. Since we know this guy, let's extract. Sometimes we are after only the probability distribution, some marginal probability distributions of the next state, right? And therefore, we apply the sum rule to get the transition model and the reward model. I hope you understand this equation. It's not really difficult. I am marginalizing out random variables which I'm not interested in, right, to obtain the probability distribution which I am. Up to this moment, everything is fine. Okay. All right. So we then said, okay, fine. Let us just assume a small grid world of 4 by 3. So in total, we have 11 states, as it is shown over here, where we do have an agent. This agent is going to start from some initial state. Okay, the state is basically the location of the agent, right, in this kind of world. And depending on certain settings, configuration of this kind of world, the job of the agent is to do what? What is the job of the agent? Yes? To maximize the reward it can get throughout the interaction of this with this environment. We have terminating states, +1 and -1 over here, right? These are two terminating states. And obviously, if someone before this class showed you this, right? And said, okay, what is the best scenario, right? What is the sort of best possible action that the agent can take? Many of you will plot this guy. Some of you will also plot this guy. Without really even sort of knowing anything about the optimization problem, all of you must have plotted the solution, right? So we need to understand now how the solution will be obtained from the computer. So we said, okay, fine. We are facing a stochastic problem, okay? Stochastic environment. This means that the state transition model is complying to this probability distribution. I can go towards my intended state, whatever my intended state, east, west, whatever, south and north, right? with probability 80%, but with some small probability, I can also go sideways. Okay. This is basically your P of S prime given S comma A. And how are you going to represent this probability distribution? Obviously, you're going to present it as a lookup table, right? Because everything here is the states are discrete and the actions are also discrete. So this is in general kind of a volume. Let me get rid of this thing over here. Okay. So in general, this is a volume of S prime. Every slice of this volume has an S prime axis and an S axis, right? And this table over here. So you told me last time that if you are to calculate the first row, you will calculate it like this, and the same way you will calculate all other transitions, right? If the action is up. Okay, so effectively, the first row says that I'll go here with a 0.8, I'll stay here with probability 0.1, and I'll go here with probability 0.8. And I can do that for all 4 possibilities that I have in this specific row that I'm in, for all remaining actions. And then I'm done with the tabulation of the state transition model. This is what we will assume in MDP to be known, given. Remember some stuff that was given to us in the HMM kind of model as well. Obviously, not everything will be given, right, in the future, but right now it is. Okay. And we have said, okay, fine. But there are some numbers written in this small grid world, like this minus 0.04, right? Obviously, you saw the big numbers, the +1 and -1 in the terminating states. There are also some other numbers written in the other cells of this grid world. These numbers are manifestations of the reward function. Okay. So the reward function basically says, okay, if you are here and you, let's say, transition to this state, if the environment allows you to transition to this state probabilistically, of course, you will get a small negative reward. Someone says, no, I don't agree with that. I think you should be getting a small positive reward because you are moving. But no matter what, this reward function, what is a function? The function of the state you are in, the action you took, and potentially the state that you ended up, is up to you to design. Okay, so this reward function has significant effects on the behavior of the agent. Because obviously, as I think I told you last time, if this was a small positive number, what would be the agent to do? To maximize the return, the rewards over a whole range of experiences. What should do? Move around here endlessly. This, if you do it like 100 times, you are far exceeding the +1. You will do it by terminating. So the agent will not terminate at all. Again, the interaction. All right. So we kind of had some unfortunate symbols over here, right? That somehow seem to many people believe that kind of complicate this whole treatment of the problems we're in. But this expectation, it should not be something from outer space. I hope you understand that in a discrete probability distribution, let's say, the expectation of X is given by what? X times Q of X. The expectation of F of X is summation over F of X times Q of X. So there is, basically what is always the equation has to be translated to English. If you cannot do this translation, it means that you cannot understand what this equation means. And therefore, you cannot understand the solution because many of the solutions will be based on these equations, which unfortunately has expectations. So the question for you is, what this equation is telling us in English? It's telling us that effectively the reward function, and let me go a little bit further down where I have this, because the reward function is actually giving us the rewards that you will get over time, right, over this whole period of interaction. This return is a fundamental quantity. I hope you understand that. It's a fundamental quantity. And also, we will meet now something that involves an expectation of this random variable. First of all, why is this is a random variable? Because these guys are random variables. Do I know what I will get when I take an action? Well, I do not know because I do not even know where my S prime will be. Do I know after I took that action, I end up in some S prime, what I will, when I do the following action, the A prime, that I will end up in some S double prime, and I'll get a reward? Then, do I know that reward? No, I don't. Right? Because the environment is again stochastic, and also I am exercising some random policy potentially as well. Okay, two sources of randomness, the stochasticity of the environment, and the other is that my own actions are not deterministic from a state. Okay. So all of these sort of at some point when we start developing now the optimization problem statement, which is needed for us to find a solution, are going to give rise to these expectations. And we already have some kind of elements in this kind of summation of rewards that I will get into the future, right? By introducing this discounting factor. What is this discounting factor is doing? It is
dropping the reward.
It is discounting future rewards because I do not want to consider all possible future rewards because they are uncertain. So I'm trying to create some kind of limit that by this less than one discounting factor. The discounting factor could be all the way very close to zero, which means that I would not really care that much for the future. Or it could be very close to one, which means I do care. And therefore, by saying I do care, I mean that my own ultimate policy will be affected by that gamma factor, for sure. Okay. And I gave you an example with sort of basketball when it came to treating this as an infinite horizon versus a finite horizon problems. Okay? Infinite horizons are the problems we will be dealing with, despite the fact that we will be terminating. It's just that the horizon will be infinite because no one imposed a specific deadline to us to finish the interaction by the specific deadline. Okay? So we finally defined a policy, which I already have covered during this kind of review. And we are about to start writing down the objective function. You told me that we need to maximize some quantity, some maximize of the future rewards. What form this objective function will need to take that we have to maximize? And if we write the objective function down as an equation, then we will see what algorithms can solve it, can maximize it. Could be a stochastic gradient ascent, could be something. I do not know right. Okay, so let's write down. This is lecture 12 for 25, 24, 20, 24. This watch is 26, 24. Okay. All right. So let's see. I want to name these value functions. These objective functions, I will call them value functions. And they will represent something. They will tell us some story about states and actions. Okay. So let's write down first of all, we're going to have two value functions, what is called the state value. A function is always there. And we will symbolize it with small letter v, pi of s. The small letters are mandated notation-wise, not that they have to follow them, but most of the people follow them because there will be capital letters as well later on. Okay, so we'll use capital letters for potentially estimates later on in reinforcement learning, and we'll use small letters right now because in MDP we will be able to calculate this expectation exactly. Okay, some things that are going to show up exactly. Of course, there are some issues that I need to address. So let's first of all write down the definition. V pi of s is equal to expectation over pi of gt given st is equal to s. Is equal to expectation over pi of summation from small letter k is equal to 0 to infinity, gamma to the power of k, r t plus 1 plus k, given st is equal to s. So basically, it says the following. First of all, the state value function is a function of what? I wrote state value function. The function is function of what? The state, yes, it says here. State. So if it is a function of the state, for every cell that I have in this kind of grid wall here, in this kind of room, there is a value. Value of being here, value of being at the end of the room over there, value of being next to the door. Okay, there is a value. There is a numerical quantity, right, that this equation will calculate for us. Okay, not as we see it right now, but we will see how it will calculate it. And this value represents what? What is this equation is telling? It's an expectation. If I am executing a policy pi right now while I'm moving in this room, right, and I have a termination state at the door, exiting the room via this kind of door, right? If I'm executing this kind of policy, I am going to go here, there, and so on. I am going to form various kind of trajectories, right? Some trajectories like in the way that you understand a trajectory, like a sequence of states, by taking these actions that the policy told me to take. Remember, the policy could be stochastic, right? Could be random. So it's a discrete probability distribution. I'm sampling out of this discrete probability distribution to come up with the specific action I will commit myself doing at this specific moment that I am in here, in this state. So I have four possibilities. I'm doing this, and therefore I am transitioning. I'm now changing to S prime, and I'm picking up a reward out of the environment. The environment sends me the reward. So the environment will send me the reward from now to infinity. As I told you, I'm moving endlessly in this room without exiting the door. So I'm discounting what step I am from the moment I start to the 100th step, right? I'm discounting every step on the way. I'm discounting it more and more, more and more. The rewards are just coming back to me from the environment. And this expectation is basically tells me that because you have stochasticity, right? You are going to execute. You're going to account this stochasticity. This V pi of s will be some kind of an average of what? Average of all the possible rewards that you will get out of or return, as we call it, right? This is basically the definition of a return, by the way, that you will get from t all the way until you terminate or not terminate. Okay. So there's going to be a numerical value that we need to understand how to estimate that value, how to calculate it. Okay. But first of all, I want to double check that you understand what this equation is telling you. Yes.
So essentially, it's like the return you collect over every single possible path.
Yeah.
To infinity.
So here,
Going left, like
yeah.
path.
Yeah. So you can form this as a kind of a drawing, as a form of a trajectory. From T to all the way to, let's assume that both of the trajectories ended up terminating, the experience. And therefore, you're going to average all of these returns that you get across all these kind of trajectories. As we will see, because we know everything, right, we are not estimating just based on this finite number of trajectories, right? Although in real life, if I give you this is probably what you will do, right? You do some form of what we call Monte Carlo estimation, right? But because we know everything, we will be able to calculate these values very exactly, this expectation very exactly, right? By replacing the expectation with the summation formula that I went through that just a few moments ago. Okay, so don't be afraid from this expectation sort of quantities over there, right? But because they will be replaceable and computable at this moment in time, at least. Okay. So let's continue. Expectation over pi, RT plus 1 plus gamma, RT plus 2 plus gamma squared, RT plus 3 plus ... even ST is equal to S is equal to expectation over pi RT plus 1 plus gamma. I'm taking gamma out of the parenthesis. RT plus 2 plus gamma, RT plus 3 plus ... ST is equal to S, close square bracket. Nothing happened. I just wrote exactly replace the summation over the infinite terms with exactly what it represents. Okay. And then I took the gamma because I want to tell you I am not going to do the derivation of this, okay, but I'm going to write this. We can show that the V pi of S is equal to expectation over pi of RT plus 1 plus V pi plus, gamma. Gamma is important here, gamma. Oh, messed it up. Plus gamma V pi of S prime. Oops, I forgot the ST is equal to S. Given ST is equal to S. So this equation over here is known as the Bellman, from the guy who invented it, right? Expectation equation for V pi of S, for the state value. And the derivation is in my YouTube channel. It's around 25 minutes to watch. Okay, but I'm doing it because I had nothing better to do that afternoon, right? So I just did the derivation of this thing, and you don't have to watch it unless you are somehow go through some kind of dark moment. But the equation is actually, despite it's not difficult to show it, but it tells us a very kind of interesting story, which I'll try to dissect right now. And I'll try to dissect this story by effectively pointing out two things that are happening in this equation. It connects the value of the future state, whatever the future state S prime is, to the value of the state you are in right now. Okay. Please make sure you are following, because if you don't understand this, you may just well call it a day. Nothing else will be understood. Okay. So this is the key moment. Try to follow this discussion. Okay, so to understand, if you like, in a bit more graphical way what this thing is doing, I'm going to start drawing what Saturn is also drawing in his book, which means I will draw some kind of a tree structure, and transversing these trees and understanding what they show is also kind of important, goes hand in hand with the equations, the Bellman equations. There will be 4 Bellman equations. We just saw the one right now. There will be another 3 coming. But understanding the first one is always more important than the 2, 3, and 4. Okay, so I'm going to draw a tree that starts with this kind of state S that, by the way, has a V pi of S associated with it. There's some numerical kind of value. And obviously, out of this kind of S, I am going to represent with hollow small, with solid small nodes, actions. These are action nodes, these are state nodes. Hollow nodes, state nodes, solid nodes, action nodes. It says here, out of state S, you can take, let's say, whatever, 4 actions, as we had it in the grid world. Okay. Let me draw it like this. Up, down, left, right. Okay. Who is going to allow you to pick up one action? Obviously, the policy. You're going to sample out of this discrete probability distribution a specific action, and when you take it, now Saturn does not introduce this node, which I will also not explicitly draw over here, just to be compliant with it. But you can imagine the presence of an additional node called, let's say, the chance node in the literature that says, okay, it is really the chance node. Let me draw it. Okay, doesn't matter. Let me draw it like this. And out of this chance node, out of this chance node, let's say the environment will, using the state transition, let me introduce a transition as PSS prime, the probability of reaching an S prime from S. Remember the 0.8, 0.1, and so on example that we have seen kind of earlier. It will arrive to some kind of a number of S prime nodes. Could be 3, could be 5, could be 100. Doesn't matter. Okay. So we'll see now why this node is kind of also useful to put it mentally. Mind you that in some instances I'll be drawing this. I will still be writing this PSS prime here, and I'll still be writing policy pi over there. Okay. So either of the 2 representations is okay. But if you read Saturn's book during the summer, this is the representation you will see in terms of meaning. So what this Bellman equation is suggesting? Well, it suggests something pretty straightforward. If the S prime state that you will end up has a value, right? There is a way to calculate this V pi of S from the V pi of S prime. A very simple story, it says. We'll see now how, with an example, how to calculate it specifically. But it says a very simple story. Like, for example, we can, this diagram, by the way, is called the backup diagram for V pi of S. There will be other backup diagrams illuminating the story that the remaining three equations are telling us. Okay, so now that we have some understanding of this estimation kind of problem, I think if I bypass the derivation of this thing, I think it's time to go back to this grid wall problem that we had earlier and try to come up with a solution to estimate using this equation the state value for all states, for all 11 states that we have in the problem. Why we are trying to estimate the values of the states? Because maybe if I know the values of the states around me, maybe I can adopt some kind of heuristic and move to a state that has a higher value. So intuitively, it kind of makes some sense to know that this state over here most likely will have the highest possible value for the specific problem of terminating by exiting the room, as compared to another state over there. Okay. And when you are in the middle of the room, most likely you will see higher value states in some kind of a beam that it is leading into this type of termination, as compared to a -1 termination, which is that at the top. So we will be calling these problems of estimating the values, prediction problems. And the question is evaluate the grid wall problem. Mind you, as you go through the site, there are many grid wall problems, different grid wall. There's only one, there are many, right? So make sure that when you read, you kind of make sure that you understand which grid wall problem you are referring to, these calculations, for example, right? There are some calculations on the site as well. All right, so let's see. In this kind of grid wall problem that I did last time, I want you to tell me what is the value of the state S33, okay, which is just before the door, okay? So I will draw first the S33 that I want to estimate the value, and out of all possible actions that I can take, I will fix the action right now to go right in order for me to terminate. Okay. If you remember the grid wall, unfortunately there are two different parts of the board, so I cannot really show you at the same time. But let's assume that I am fixing A is equal to right. This is the node of the right action. We have 4 actions, okay? And if you execute the right action, if you commit to the right action, you will end up. If you execute the right action, you will terminate with probability 80%. Therefore, you can reach S43. Remember, S43 is going to be one of the nodes. S33 will be another node because you can go sideways with 10% probability, so you can go against the wall and you remain to this same state. And another state you can reach is S32, right next to the -1 state. Okay, I hope you recognize this possibility. Yes.
Why are there 4 actions then in the tree?
Oh, sorry. Is it 3 actions? Usually I confuse with taking 4 actions in this kind of room. Okay, so I will delete one. Well, hold on a second. The three actions, the three actions means whatever direction you are taking, you're going towards the intended state, and you go sideways in remaining two. So I can definitely take the intended state to go north or south or east or west. So if I go west, I will go to my transition model, and then I will execute that transition, whatever thing that I've involved these three are. So don't confuse this guy over here. This guy over here. This is not the possible actions I can take. I can take any of these sort of intended actions, and I can go sideways. Okay. But the intended actions is still 4. All right, so let's leave this branch. Not that it's very important for our discussion. So you remember the states is S43, right? Termination S33 and S32. These are the 3 possible states out of that right action. Obviously, I can go take any other action. I will have another expansion and another expansion over here. So for all possible actions that my policy allows, the tree is going to expand. The whole breadth of the tree is going to expand potentially, right? And as I'm taking more and more actions in the future, the whole depth is going also to be experienced. So the tree grows, despite the fact that I'm just limiting the discussion now to this specific action at this specific moment in time, in this specific transition. So, for example, if you are to go to the second action could be to go over here, right? To go left, then you will go here in S23. That's a state that we have not seen before, right? You will remain in S3 again, right? And then you will actually go. Where are you going to go? S3, S32. Yes, you can go also to S32, just like before. So some of these states, you will see that in a moment. Some of these states will show up in many, I will call it sideways to that kind of 3 expansions, right? But we'll come to that in a moment. Okay. All right, so let's write down the equation. So V pi of S33 is going to be some R, immediate reward, plus gamma. The probability of S43 given S33, comma, A is equal to right. Where is this probability coming from? From the transition model. Times V pi of S33. Sorry, V pi of S43, that is. Plus P of S33 given S33, comma, A is equal to right, times V pi of S33 plus P of S32 given S33, comma, A is equal to right, times V pi of S32. If I'm executing one-step transition, right, I'm going to get an immediate reward, whatever this R is, who cares? At this moment, we have a numerical value for it. And you are going to pick up, according to the Bellman equation here, right, some value by just moving into the corresponding S prime state. What specific value you're going to get, right, you do not know because it's the environment who is going to transition you. Right? So on average, you'll get some average value out of that kind of transition. Okay? Now, can I ask you the following question? What do we know here, what we do not know? Do we know these guys? Do we know these guys? And the answer is yes. One is 0.8, the other is 0.1, and the other is 0.1. So we have some unknowns, right? And I can actually now, I want to ask you the following question. Can I write exactly the same equation as I wrote over here for all 11 states? Okay, I ask you the question, what is the V pi of S33, right? I can also ask you the question, what is the V pi of S32 or whatever remaining state exists, right? Would you write something like this for S32? You will write, in other words, another 11 equations. Are these equations linear or non-linear? What do you think? They look pretty linear to me. If you're just replacing the numbers over here, you have some fraction of this value plus some other fraction of the other value, or whatever that is, right? So you have 11 unknowns, right? And you can write 11 equations. So can you solve a system of linear equations, AX is equal to B, using whatever matrix inversion method you have been taught to use, right? And the answer is obviously yes. What will be the unknowns? The values. So I can very, in fact, accurately at this moment in time, solve this system of equations, right? For this kind of a grid world and come up with a value function of the grid world. Now, so let me write it down. So we can write 11 equations such as this. And we have 11 unknowns values, state values. The equations are linear, and therefore we can sort of represent the problem of calculating the state values as AX is equal to B. And now in the website, let's try to see a solution. Let's try to see how the solution will look like. Yes, go ahead.
I just want to clarify. So the R in the equation is like the reward that's picked up on that cell, right? So
correct. The moment you do the transition, whatever the transition gives you this S prime, you will pick up an immediate reward.
So like for here is whatever value is it?
Whatever value. We can set this reward function with minus 0.04, or in this case, if you go right and you end up in this, you will be +1, whatever that is. So let's look at this example over here. I hope I have this example. Let me see. Come on. Bellman prediction. So we are in the prediction section, believe it or not. So in this kind of problem over here, we have two states. Okay, we don't have the complete grid world here, although we have the notebook with the complete grid world. I just want to go through it, just a two-state simple example, right? We have two states, S1 and S2. We have a deterministic policy, not random, deterministic, that always chooses random A. This is the simplest possible thing can happen to you, really, at this moment in time. From S1, so we have two states, S1 and S2, with squares over here, and we have some arrows going between S1 and S2, right? Because from S1, the action leads to S2, and you get reward 2. From S2, action leads to S1 with reward of 0. So effectively, we have something like this. You tell me, because I don't remember, S1 and S2. One, two, three. Okay, we are okay. Okay, so what I was saying, I was plotting the final state machine kind of thing, right? So two states, one arrow, the other arrow, and basically what we have here is we have a discount factor. Let's say gamma is equal to 0.8. Okay. So our job here is to estimate the value function. How many states do we have? 2. What is the length of the value vector? 2. Right? Because it's a value function of the states, the 2. All right. So do we have a state transition matrix? Yes, we do have a state transition matrix. Deterministically, the moment we are in S1, we will go to S2. Okay. In other words, we don't stay in S1. And then we have a reward vector of 2, 0, like what I just saw. So write the Bellman expectation equation in vector form. V pi is equal to R, the rewards, right, for this specific policy, plus gamma PV. That is basically the vectorization of the equation we had earlier, right? So you rewrite it as this, and therefore this is your AX is equal to B. This is where the AX is equal to B. And then you are computing with this kind of matrix inversion, and then you come up with V1 is equal to 2, and V2 is equal to, what is this? Solving gives this and this. And therefore, what am I writing here? Because I don't even see. V2 is equal to 0.9 V1. Does it make any sense? Does it make any sense? V2 will be equal to 0.9 V1. Yes, because it's only through the transition that you are picking up the reward, right? So you need to go to S2. Now, as I told you before, every time you have these matrix inversions, right, probably you don't want to follow that approach, right? It will probably blow up. Not in this trivial problem, but in general, right? In many problems, large problems and things like that, because of the usual numerical issues with matrix inversions. So what we are doing over here is we are solving this system of linear equations with an iterative approach, and we take advantage of what is a contraction. So you will see that in the literature, it's not something, you treat it like a parenthesis. As it turns out, the Bellman expectation equation for the state value is a contraction. What does it mean, a contraction? I'll give you an example over here. you have an iteration with x plus 1 is gamma. Gamma is less than 1, right? Times xk plus some constant c. Okay. Pretty much what we have in the Bellman sort of contraction. All right. So this basically, I'm making this analogy so you can actually see it explicitly. And solving this, iterating this over many times, it's called a contraction because it will go into a fixed point, right? And therefore, it will, in fact, you can analytically show it goes towards c divided by 1 minus gamma. Okay. So you can have a numerical example over here to make sure that you understand the solution. It will lead you to a 20, right? And we will follow a similar approach on the vectorized Bellman equation. And therefore, we start with some initial V0, some initial state value of the vector. We have our V1 using the same formula. The V1 goes over here, becomes V2. Are you following? V2 goes over here. Yeah. Where is the V2 here? Okay, I didn't write it like this anyway in the expressions 3 and 4, but it's exactly the same thing. And finally, you conclude on this value 10.526 to 9.47. Okay, so you want to be into S1, right? Did I say S2 earlier? That is not correct, obviously. You want to be to S1 because only from S1 you will get a reward because you will immediately transition to S2. So the value of being in S2, obviously S2 will bring you back to S1. So the S2 will have some value as well. It's not really that completely useless, right? So I think it's a very nice numerical, simplest possible example to get your head around how we predict state values. Obviously, we will expand this now to the mini grid, the one that we were trying to solve. I'm not 100% sure if this is the if this is the notebook that it will solve it for you, right? According to the mini grid, right? So obviously, it's exactly the same thing which is actually happening here. And then if you do that, this is not the same mini grid. This is a much larger mini grid. It has 35 states. And many of these mini grid environments are in the library in Python or Gymnasium. You may have heard about Gym or Gymnasium. These are the libraries where many people start to sort of teach themselves kind of simple environments, right? Like a mini grid could be some kind of a landing of a spaceship, which is, despite the name of that thing, is called lunar or something. I forget now. It's a kind of a small problem. Card pole, which is basically how to balance a pole. This gives you also some kind of information and some kind of exposure to continuous states, not only discrete states. Right. So here is so this is basically your notebooks that will expand what we just did with the two states. And then this is the iterative method as it was. So you can see here, Gym, mini grid empty 5 by 5 is 0. That's the name of the environment. We don't spend time creating environments. We just pick it out of this kind of library. And we use the sort of stuff that we just learned. We are going to start with some kind of uniform random policy with all 4 possible kind of actions. And here we are going to evaluate the policy. This is what we do, policy evaluation, come up with a value vector for that specific policy. Okay, so this is going to be a function. Okay. Now I'm trying to understand where on earth is this function, policy eval iterative. But I think the policy eval iterative was earlier. This is where the function is policy eval iterative. We have our discount factor 0.99. and some kind of an epsilon, because of the interactive kind of nature of the algorithm, we need to stop at some point. Otherwise, it will continue forever. So we stop by defining a number, like a small number. If we see that this value function does not change from one iteration to the next by more than this number, we stop. Okay. So I think this is a common thing to many kind of algorithms. Okay. So we start with all zeros. This is because we are doing iteration, I'm using capital letters now to come up with the value vector, the V. Obviously, this is whatever number is 11, I can't remember now the number of states, NS. And while true, this is now the loop that it will do this iterative way of calculating the value vector, as we have seen in the two-state example. So for each state, we go around in our mini grid for each kind of state. Perform a full backup. That is a keyword. Remember the backup that we said earlier, and now full because I have values. I mean, in order to estimate a value here in this kind of state that we are in, I can potentially pick up values from other adjacent states. And these states will also pick up values from other states adjacent to them, if you think about the mini-grid problem, right? So I'm expanding these three as long as it takes. So look up the possible next actions. So I'm looking at the policy, obviously, in order to come up with an action and the corresponding action probability. And for each action, look at the possible next states. For each action, look at the possible next states, just like what we did with the equation I was writing. If the transition is possible, calculate the expected value. That is where your plus equal sign is there, the summation, in other words, that I wrote, right? That will obviously multiply the action probability with the transition, and then it will have the R plus discount factor V pi of something. So this is just the Bellman equation right here. I will be able to explicitly do the summation now because I know everything. And if, as I'm doing this, this is where I will potentially terminate. Otherwise, the V new that I got will become V old for the next iteration. And the V old will become V new and so on as I am going through this loop. Then the loop will break over here if there's an epsilon and return the converged value function. So study this notebook, step through it, right, line by line, to ensure that you understand the evaluation of the policy. Now, obviously, this is the values that are going to be produced for every possible state. This is the value, the converged value. I should have put it as a matrix, but anyway, it was a kind of, 2 years ago. Now, I want to mention a couple of things in passing. No one is obviously writing code like this, right? So there are now reinforcement learning frameworks that are geared to address LLM, VLM, VLA type of fine-tuning models, model fine-tuning, right? So these are gigantic, obviously, environments because, and I'll just give a parenthesis here, we are not going to go into this necessarily, but I just want to tell you why this is mentioned over there. So this is like a scaling RL problems. That's a kind of a very general discussion outside of equations. So in a fine-tuning kind of model, I'm not sure if I mentioned it in this class, I'm getting kind of confused. You start with a model that is out of pre-training. You pre-train a model, like a language model, like what we did kind of earlier with transformers. You pre-train it with trillions of tokens, right? You come up with let's say when 1.5b, right? 1.5 billion parameters. Like take a small language model such as this, right? They pre-trained it, okay? And then you can potentially also fine-tune it to a specific domain. Let's assume that this fine-tuning happens, you get another 1.5 billion parameters, whatever. Even if you're using LoRa, you still get the same number of parameters, right? Despite the fact that the fine-tuning is going to tune much smaller letter of parameters than the original ones. Okay? So no matter what, you have a model now that you want to do reinforcement learning on, right? To do reasoning, for example, to be able to answer middle school math problems, GSM 8K. This is the data set for applying reinforcement learning to solve middle school math problems. So this is your question, and this is what your answer should be. You have thousands and thousands of these examples. Q&A pairs, right? So you start with some state in reinforcement learning terms called S0. What is your S0 state that you start in this specific iteration of the training? You start with a prompt. That is your prompt right here. That's your question, right? So you have a situation where you have the policy, pi. It's common to call it pi theta. Your pi theta is nothing else other than the LLM that you are fine-tuning, right? And then you are getting interacting with the environment. Right? So your job is to change this pi theta, the policy, because the LLM now is, by the way, the policy is LLM, right? So I told you the policy is a discrete probability distribution of 4 elements just a few moments ago. Now this discrete probability distribution became a discrete probability distribution over 100,000 elements because these are my vocabulary sets. Right? The job of the LLM is to feed a prompt and generate a token. Then we'll take this token, we will add it to the prompt that it generated to migrate itself to a new state, S1. So it starts with S0 with a prompt, takes an action, which means a generation of the token. The moment the token is generated, it leads deterministically to an S1. There is no state transition model here in this reinforcement learning fine-tuning. In other words, the only randomness that happens is because of the policy of the LLM. The LLM just happened to generate that token. The moment I have the token, I append it to the prompt, I am migrating to the specific S state now, right? So I will start with S0, which is my prompt. I am taking out of the very huge action space an action, which is new token something. Each of these solid circles is a new token, potentially new token. That's like 100,000 possibilities right here. And for this specific action that happened to generate, for this specific action, let's take this one. I'm migrating to S1. What is the S1 state? Prompt plus capital N. If the token is a character level tokenizer, right? You're producing characters, right? Prompt plus this capital N. Same thing. You change. How much reward are you going to assign to the agent that generated capital N? It's a big fat 0. I mean, that is not, like Well, this is kind of intuitive, right? I mean, I'm going to reward. I'm going to effectively going to give you a reward of equal to 0, right? And then again, the same thing will happen again. Let's assume this token now is generated again, goes to S2 deterministically with reward is equal to 0 again, and then after some period of time, this state that led to the termination send me back the right answer, 72. I'm going ahead and they tagged specifically just before the right answer comes. You know, this hash, 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 whatever, special symbol. That is what you need to get at the end. For that specific, if the LLM produces 72, I will give it a reward of 1. Positive reward. It may not be 1. It will be something else. A 1, let's say. So I'm having now a huge problem. Like, out of potentially hundreds of transitions that I have done, right? I have now a reward at the very end of 1, and I need to do what is called the credit assignment problem to change a huge probability distribution. This pi theta that I called it, which is the LLM, which is the probability, the posterior probability distribution present in the LLM output, because that is the one that generates the tokens. That is the one that determines the actions. So if the whole discussion here up to this moment in time sounded a little bit abstract, this does not mean that it's not applied anywhere, right? In this kind of small grid wall problems, it is applied heavily out there. So try to spend the summer to reach this point of being able to tune yourselves language models. You will do the same thing here. Another reward will be assigned here and here and here and here, potentially 0. You know, in some examples, you will not get the right answer, right? And obviously, depending on what you get, you will adjust the parameters theta of the LLM in order for you to adjust the policy in reinforcement learning terms. Hope you got something out of this parenthesis anyway. So this is basically the... So, okay, the reason I actually started this discussion is that at some point you saw kind of array being mentioned, right? These reinforcement learning problems are only manageable by very big technology companies, right? Because they are huge. They need to scale in substantial ways. And Ray is a good library to know if you want to be able to claim that you have some exposure to scaling. No matter if it is reinforcement learning or some other kind of deep learning kind of learning, algorithms and things like that, they have a library called RLib, right? So the Ray has a whole bunch of libraries. One of them is dedicated to scaling reinforcement learning. So if you want to know some framework to allow you to do something like that, that's probably Ray. Close parenthesis. Now, unfortunately, we are back to the Bellman equations. Okay. So writing down now the iterative policy evaluation. So I did the parenthesis, and now I'm going to write as a headline the iterative policy evaluation. We saw the Python code, but I didn't write the equation down. That's what I'm doing it like in a kind of a reverse order. Iterative policy evaluation, V, K plus 1. Remember, K is the iteration number of S is equal to summation over A, pi of A given S, summation over S prime comma R, pi of S prime comma R. Now, everything is kind of very clear with respect to whatever is going on here. Vk of S prime. I hope it's clear because this equation is just now gives you the tickets to tell me your value function across the whole word that I'm going to give you. again, the expectations became now specific summations because we know the probability distributions. And therefore, we can apply just by the definition of expectation, replacing it with a summation. And embedded into this kind of discussion is the complete expansion of this tree, right? That starts from this kind of state, and across all possible actions, I can expand across all leaf nodes. Now, there is one specific notebook in your, if I can find the site again, a very specific kind of notebook, which I will mention in a moment when I go now to outline the other equations. And in this kind of notebook, you can actually see for some kind of a simple example, this whole tree, how it expands with specific numerical values, right? So if you have some values over here, what kind of value you're going to pick up over here? So you have an example, a non-trivial example to go through to understand how effectively think about it like backpropagation. Obviously, we're not really applying a chain rule here, right? But you backpropagate the values in subsequent states to calculate the value in this state. These algorithms are called dynamic programming algorithms. And most of you must have gone through a course in algorithms. Anyone who has not gone through, who has gone a course in, who has already taken an algorithms course? Okay, so all of you. I mean, the instructor must have covered dynamic programming, right? I mean, because it's like, kind of foundational for these reasons. Okay. It allows you to efficiently calculate problems such as this by breaking a problem into many sub-problems, right? So the sub-problem over here for exiting this kind of room is kind of trivial, right? I mean, I need to do this specific action to exit, right? So I know my optimal kind of path. We need to discuss now shortly about optimality. So if I have solved this problem, perhaps I can solve this larger kind of problem, and so on and so on. So if I start kind of backwards, I can actually see elements of what we are discussing here. These are all Bellman dynamic programming kind of algorithms. Okay, so I know how to evaluate a policy. Now, in some instances, the fact that I have the values of my kind of states may not be enough. Yes, go ahead.
In this equation, why do we use the gamma? So this
the gamma is of course missing, which is kind of embarrassing, but it has to be there. Me too. Write my notes as well. What I was saying that even if I have the value around me, from a state I can execute, let's say, a number of actions, but at the end of the day, this does not mean that there's only one action that is best, right? So what I'm planning to introduce now is I'm planning to introduce another form of a state value, but I call this state action value. Not only I'm capturing the value, I mean, with that Q, I will associate this, as I will call this kind of values, I will associate them with these nodes now. How much valuable is this action if you are in S33? How much valuable is this action if you are in S33? This is the question that this next function, again, supported by a Bellman equation, will give us. Okay. And as you can understand, these Q values, as we call them, are far more informative to tell me where to go. Because if I have multiple Q values here, I can say, well, apply a greedy scheme and go here. Because I know the value of each action, if I'm able to estimate it. Which, of course, I am going to still be able to estimate it using another form, equivalent form, in fact, to this backup. So I'm going to define now the second one, which is called the state action value. state action value, which I will symbolize by Q pi of S comma A. And I'm writing that the Q pi of S comma A is equal an expectation again over pi of RT plus 1 plus gamma V pi of ST plus 1 is equal to S prime, given ST is equal to S. But now I am committing to a specific action A. So it is in the conditional. Okay. So I can write it because, again, for exactly the same reasons, I can write as a summation of S prime comma R of P of S prime comma R given S comma A R plus gamma V pi of S prime. And you can actually show that the V pi of S, as you understand from the Bellman expansion, again, the tree, is so this equation, but also this equation is the ticket for me to be able to evaluate the Q S comma A for the grid world, which is now, in terms of the tree, if I'm in this kind of state S, and I'm actually facing a set of actions as a choice, of course, by following policy pi, every single action is associated with a Q pi of S comma A, a value, in other words. And out of this, I am transitioning to S prime out of an action that I'm committing. I'm picking up a reward, let's say R, and I'm picking up a specific kind of value. Effectively, the second equation is connecting the value of V pi of the V pi of S, which is up here. I hope it makes kind of some sense. It is picking up as an averaging of the values of the corresponding actions that can be taken out of the state S. That's the second equation over here. Very intuitive. Okay. So you can back up from Q to V pi. And the same way, if you know the V pi of S prime, and then look at the first equation, you can come up with the value of being in this, taking this action from state S. Because by taking this action, depending, of course, on the transition probabilities afforded to you by the transition kind of model, you and the reward that is actually given you, you will you can determine your value of that action. So backups are present also here. And therefore, if a backup is present also over here, following the same sort of approach as we have done earlier, we can come up with the Q values as well. Although I'm not going to expand more on that, other than, of course, the fact that I have a corresponding kind of notebook that is doing so. So I will show you what I showed you earlier, just a few moments ago. Yes. You can understand that in this kind of notebook, we are also doing this. So we are definitely able to estimate the Q values, right, out of the V values that this specific action is lead us to, can potentially lead us to. And these are the chance nodes, by the way, which I told you that sometimes you can put them there explicitly because these chance nodes that are the PSS prime is right here. There's some probabilities. Right? Two potential S prime states, each one has its own kind of probability. Yes, of course, have the ability to do the expectation. So a fully numerically solved example for depth 1, depth 2, depth 3, depth whatever you want. Every depth that goes on brings more and more information. You expand the tree, look at the number of states exploding. This is depth 1. Very simple to enlarge the video monitors and see out of this kind of values how we can come up with this, how we came up with these two values. So this specific rewards quoted also here. Depth 1, depth 2. I have just 2 depths. It's fine if you just go through that. I think that's fine. I cannot do everything right now during the lecture because this is a numerical example. It requires you to step through the code and understand what on earth is going on. Right? Validate the numbers are correct. Okay, so there are some other stuff which that's not really important here, but I want to stay on the remaining 2 Bellman equations, which will also be the ticket for us to calculate the desired solution, which is the pi star. After all, I'm not after Q values or V values. I only use them as objective functions, as part of objective functions for me to calculate the pi star. That's all I'm interested in. As it will turn out, the last 2 Bellman equations will give us a solution, are nonlinear, and therefore we'll need to apply special algorithms that are solving them for us. The special algorithms are going under the headline of generalized policy iteration, and we will end this lecture with an example of the policy iteration coming up out of this lecture with the ability to estimate a pi star, right? Out of the grid world or whatever problem someone throws at us. Okay. So, with that said, that's the point where you need to fasten your seatbelt because this discussion happens a little bit it's a bit loaded. Okay, so I'm going to title this discussion Optimal Value Functions. Stay with the V and Q, but now we'll call them V star and Q star and optimal policies. The previous discussion was okay, I mean, with just a single review. So I'm claiming the following. The best possible, and that's why I will symbolize the best possible value function I can ever get. Following the best possible policy I will get into with an environment, with interaction with the environment, is going to be symbolized with the VISA. Best policy, the best possible value. There will also be a Q star. Okay. And the reason why there is a Q star is that obviously there is an infinite number of discrete probability distributions I can do in this specific grid world that I'm in. Okay. There are 4 possible actions I can take. Each one has its own floating point number of the probability of following action forward, backwards, left, and right. Okay. So there's an infinite amount of policies I can actually do, and but the pi star may not necessarily be unique. The one that I'm reporting, there may be multiple kind of pi stars, right? But definitely one of them will give me the V star, the optimal possible value that I can ever extract out of an environment following this policy. So this is basically equal to max over A of Q pi star. Sometimes I'm calling this pi star to tell you that this is the optimal policy of S comma A, which is also max over P, V pi of S. So I did not do anything really, I'm not really claiming anything dramatic kind of here. All I'm claiming is that if I am in state S and I know the Q pi stars of S comma A, if I know the best possible values of my actions, right? By taking, if you like, the max, it will lead me to V star, that is, not V pi, V star first. In other words, what I'm saying is that the value, that's a translation, the value of a state under an optimal policy must be equal to the expected return for the best action from that state. In other words, what I did is I kind of continued from here. I continued from here, and I wrote this equal to max over A expectation over pi star of GT given ST is equal to S, AT is equal to A. And obviously this is equal to the well-known to us now return, max expectation over pi star. If you replace the GT with RT plus 1 plus gamma P star of ST plus 1, given ST is equal to S and AT is equal to A. Nothing to be afraid of. I mean, I think I have already mentioned this so many times that it's almost like a second nature to write it down. Just the max is here is what is troubling us, which I need to address. But this is basically S comma R of P of S prime comma R given S comma A of R plus gamma V star again of S prime. This is basically the Bellman optimality equation for the V star, for the V star. Call the Bellman again. Equation. And basically, it basically says the following: if I am to ever get into a V star by being in this kind of state S, I should not screw up my next action. I mean, if I am to exit the room and I go over here, right, then you can understand out of being here, there is no way I will approach the V star. Because to approach the V star, I should have gone here towards the exit. So nothing dramatic is happening by just this kind of statement, right? But the max operator, the max is a nonlinear operator. We cannot fight it with AX is equal to B. So we have to invent algorithms that are actually solving iteratively nonlinear equations. And algorithms have very famous names because out of this kind of algorithms, a lot of algorithms that you are hearing out there from out of policy iteration and value iteration, a lot of algorithms that we are hearing out there in terms of reinforcement learning, like in the next kind of lecture, like policy gradients, PPOs, GRPOs, the whole paraphernalia of acronyms, right? They are all coming from outside. Okay, so the tree is expanding both in terms of concepts, like if you understand the foundations here, you can actually expand into the many acronyms that are littering this environment. So out of these two algorithms, the policy iteration and the value iteration, I want to mention something that as well that I have here as notes. Come on. For each state S, we go through all policies I and pick up the policy that maximizes V pi of S the maximization also have another note. The maximization is done independently for each state, and we may end up with different policies that maximize V pi of S for the states. In other words, I can get a V star of S by following this action over here, but also potentially not for the specific problem, of course, because so evident, but for another action as well. So in the grid world, I may have multiple arrows that can potentially lead me to V stars, not only one arrow. So I can actually suggest that for specific values of rewards and things like that, as I told you when I first presented this kind of grid world, this could be one policy with the corresponding arrows deterministically pointing like what I'm pointing right now. But this also could be another policy that will lead also to this star. I'm not saying that this with specific parameterization, this will be it, but for some states, I can go here or I can go there, left, right, for example, over here is still, both of these actions may lead to, either of these actions may lead to this star. So enough with the theory, and let's now try to give an example of how to apply, how to at least, just like what I wrote earlier with the S33, just like what I did earlier with the V pi at S33, I will do now with a recycling robot example, not a grid world, just a different kind of example, which is also inside Satos's book. And this kind of environment has a finite state machine, and I need to write down specifically the V star of a state. If I write down specifically the V star of the state, at least I have it in writing what the algorithm should be doing, not what the algorithm should do, at least the equation I need to maximize. And then what the algorithm will do, we'll see. But let's do the same thing as I did earlier. So I'm now suggesting I'm going to go through an example called recycling robot example for expressing the V star of S. Okay. So the example is unfortunately elaborate in a sense that there's not really anything dramatic going on here, but I need to draw the FSM. Okay, I need to draw the FSM, which means I need to find it somewhere. The finite state machine that you see here. But before I go and start drawing it, I want to present the problem. I need to present the problem. So you have a robot that it is moving in this kind of room, and there are some cans on the floor, and also some students which are also happy to give the can for the robot to recycle. Okay? So the robot should pick up the cans, and the robot is also battery operated. And at states in this problem, we're going to have two states. The battery state of the robot is going to be either high or low. This is clearly shown over here. Out of each state, there is a number of action nodes, as you can see, as we were representing them with solid circles over here. Right? So in the high state, the robot will wait for you to give it a can. If you hold it, right, just give it in. Or it will search the room to find cans to recycle. It will, out of this state, if it searches, the battery may be depleted and transition to the low state. Okay. Now, for every row, we have written over here the values of interest. For every row that I was drawing, right, I was writing the transition probability, comma, the reward that I'm going to assign for this specific problem. As I told you, it's an MDP problem, and therefore, everything is given to us, the reward function and the state transition. And when it reaches a low state, it better recharge. Okay, we have a recharge kind of action, or it can wait there, or if it will continue to search, it maintain to in the low state. Okay. So this is the final state machine. There is one keyword, a key sentence in the description. If I remember right, I will find it now. It's a long text in the description where effectively if you continue to search while you're in the low state, apparently you will run out of battery. And then someone has to come and rescue as a robot to plug you in the wall. If you see it before me, just let me know. But there is somewhere. Oh, here it is. The rewards are zero most of the time, but become positive when the robot secures an empty can, or large and negative if the battery runs all the way down. Whenever the robot is searching, the possibility exists the battery will become depleted. In this case, the robot must shut down and wait to be rescued, producing a low reward. Another sentence over here. So just to understand the values behind a little bit, the intuition behind the values are search, are rescue, or whatever there is. There's -3 over here. That's the large negative reward in case our battery is depleted. You are in low and you continue to search. You remain in low, but you will deplete your battery. That's the wrong row. I'm not going to solve it. Okay, I have not read all the text. I forgot the text, but you, it's your responsibility to read it. Okay, and understand this -3. Okay, I tried to explain it. It's a failure. Okay, but no matter what, this is the reward. Okay, so we will solve it blindly following the lookup table. Okay, but it's intuitive if you read it. I'm moving for the interest of time, so I'm going to write down the recycling robot. So I am going to suggest that the V star of S, according to the Bellman optimality equation, that is max over A of a summation from S prime comma R, P of S prime comma R given S comma A of R plus gamma V star of S prime. Do you agree? That is the equation that I wrote earlier. Okay, so I am going to use the following notation. Search. Unfortunately, I'm going to use S again for the, so don't confuse the two. Wait, I'm going to use W, and recharge, I'm going to use the RE. Okay, this is the notation I have in the, I think in the notes over here. So I am writing this equal to max, and inside the max of how many actions I can have for, so I have two states. I have to pick up a state that I'm evaluating the V star. I'm evaluating now the V star high. I need to evaluate also the V star of low, of L, in other words, to be complete. But right now I'm just going to do one and move on. Okay, so I am writing down max of P, and unfortunately, I don't have the notes to copy the fine state machine, but I will transition between the websites. So I am in high, okay? So I have only two actions. So you, inside the max square bracket, you will see a comma. The left-hand side of the comma will be for action search, and the right-hand side of the comma will be for the action wait, okay? So I am writing down, okay, so I'm writing down P of high given high, comma, let me do SC to distinguish from the state. SC for search, right? R, what is the reward function? Has three elements. High, search, high, plus gamma, V star of high. Close the square bracket. Plus, now mind you, there is there are two possibilities for search, right? The two possibilities is either you'll go back to high, which I just wrote, I think, right? Or the search will lead you to another S prime, which is low, which I need to write. Because I had a summation over S primes, I have to have a summation, right? I have two possible S primes out of high itself and low, as you can see from the FSM, from the final state machine. Okay. So I am writing now the plus P of S prime low given high, comma, search. Yes. R of what? High, search, low, plus gamma, V star of what? You tell me. V star of what? S prime, which is low. This is your comma. So I'm not really doing anything. I just copy the Bellman optimality equation. I interpret it for the specific FSM. I'm not doing anything intelligent here, not yet at least. So the comma is for the other. The comma is for what? For the other action out of the high, which is the weight. This action leads squarely back into the high. So I only have one term. I don't have a summation over here anymore, right? So if you get confused about this kind of loops, you can unroll this final state machine into a tree, and then everything is going to be very clear because you're going to have a variety of future states and so on. But right now, there's only one future state, high. So therefore, I'm just going to do exactly what I wrote there earlier. So this is comma, and then I have here P of high given high, comma, weight, W, right? R of high, comma, weight, comma, high, plus gamma, V star, high. Oops, that's too large of too too large of okay. There is nothing. We'll just copy and paste. That's it. I have now one equation like this, and I'm going to write, which I'm not going to, V star of low. V star of low. I can do exactly the same thing. In fact, your website has the V star of low. As a practice, write down the V star of low on with your own brain, and then double check that the V star of low is the one that Saturn has also as a solution. These equations are, do I know this is a number? Do I know this is another number? So I have V star of high and V star of low, two nonlinear equations with two unknowns in a specific problem. And therefore, I need to, because of the nonlinearity, I need to invent ways that I can solve this. Okay. As we will see, still the concept of contraction is going to be with us, right, to an ability to solve it, but this solution is going to go through two main algorithms called policy iteration and value iteration. Out of the two, value iteration is going to be the more pragmatic one, but it's good to know both because you can understand value iteration only when you understand policy iteration. So we'll go with that trajectory. In the next 20 minutes, I will be done with both. Okay, not necessarily, but I will try at least. Okay? So let's move on. Okay. Don't have any notes here, so let me treat this. So this is called dynamic programming algorithms for V star and Q star, and of course pi star. These algorithms will lead us to the optimal values, not necessarily only state values, but also state action values. But at the same time, will give us with one stone, two birds, or no, with one stone, two birds, will give us also the pi star as well. Okay. Right. So let's see how it will work. I'm moving now to a new section, believe it or not, called policy iteration. The policy iteration have two discrete, two stages. The first stage will be a policy evaluation. I want to come up with a pi star, so I'm going to start with some pi. Okay, some policy. I will evaluate this policy using the well-known. Remember, the policy evaluation was a linear iterative approach, blah, blah, all the discussions we had. I'll evaluate this policy. This is an iterative approach we just a few moments ago. And then I will do a policy improvement step. For these specific values which are around me, I will select the action that leads to a better value. A heuristic? Yes, it's a heuristic because I'm facing a nonlinear system of equations. I need to do some algorithm there, right? Including the greedy heuristic algorithms that we're all familiar with. Okay. So I'm going to do that. That's all. As it turns out, if I represent with a line, that's pure fictitious, right? If I represent with a line the values I can get out of the value vectors, right, that I can get out of the policy, for, let's say, think about the greedy world, for example. If I do this, starting with some kind of policy pi, I evaluate and arrive here with some kind of value vector. And I apply the greedy approach. I'm hitting now with the greedy approach, as we'll see soon, another policy, because the policy changes. I eliminate some of the options now because I want to go into the higher kind of values. Then I evaluate this new policy and do this repetitively, I will converge. Okay, the convergence proof, I don't care. I just believe it. Okay, and I will denote the converged values as V star and pi star. Okay, this is in a nutshell the policy iteration scheme, and we'll see how this will be done numerically right now. Okay. Now, I have a grid word. I told you some of the grid words are from this example, this environment, some others are from the other environment. So it's not the same as we did in the first part of the lecture, but it's a different kind of grid word with, I don't know, 14 states here, numbered as shown. Some kind of rewards, some kind of uniform, kind of random policy, like 1/4. And I'm actually starting to do this thing. Okay, I'm starting with some kind of random policy and some initial value vector, okay, or matrix, whatever you want to call it. And I am using the policy evaluation formulas, which is for this specific policy that I gave you, the purely random policy, tell me, give me the new value vector. Right? So I'm starting with some policy or random. I'm calculating now the new value vector. This is the new value vector for this specific policy. Iterating over many times, I conclude on this, but this is not trivial, right? Because lots of things are zero. And then we can understand that these are the terminating states, that the values are zero, and these values are -1. So, well, if I apply the greedy approach, the greedy heuristic on this one, I am eliminating some actions from these two adjacent nodes. Now I have a new policy. Go ahead and reevaluate that kind of policy. Are you following? Right? I'm eliminating some action. So I'm evaluating this policy once again, running this kind of iterative kind of approach to come up, which, by the way, it's also shown here for some of the states, right? So as an numerical example to understand the values that we are getting, I'm arriving to this new value for that specific policy in the previous stage. Well, by the way, there are some second decimal digits which are not shown here. So don't be confused as to why you are eliminating this. This is exactly the same value. There are some second order digits that are not shown here. So I'm doing another greedy. And therefore, from -2, I need to go left, get into the -1.7. And from -1.7, I need to go left to go into 0. And I'm going to do that for many iterations. I'm doing this exact, and I'm converging. As I'm doing this exact thing, I'm converging. And at some point, the policy will stop changing. Despite the fact that the value will continue to change, I have not really reached necessarily the same, the V star yet, right? If I continue doing that, I'll pick up at the end of some iteration 3000, let's say, the pi star and the V star. Are you following? I'll double check that, right? But it's very unlikely that this is where I was anyway. I don't understand why this is not working, but can you try if someone is on the internet? It should this notebook should be part of the ENGE AI agents notebooks repository. Let me know if you cannot find it. I'll double check also tomorrow or the day after tomorrow. Okay, but you should be able to find it. Apparently, there's some authorization, something like that. Okay, so let's move on. This is the policy iteration. So you should be able to launch this and step through this in Colab, and you'll get the solution that is shown here by hand. Yes.
So the V star, if I'm understanding it correctly, the perfect solution. Is that right?
The V star is not a solution, the pi star is a solution, but the V star is the best possible value we can extract out of this environment. Okay, because we are following now pi star, right? Ultimately, we are starting to follow pi star. V star will stop changing significantly. And then at some point, at the end of our iterations, which are different iterations than the evaluation iterations, mind you, there are now two loops going on, right? The evaluation itself has a loop because it was the loop that was evaluating the policy, the iterative approach. And now there is a second loop over here that goes between greedy and evaluation, greedy evaluation, greedy evaluation. And finally, we end up with both of them at the end of the day. Yes.
Does it matter where you start from? Like if you
No.
always follow pi star,
No.
will you reach the same outcome?
No, you of course, if you knew pi star, of course, initially, then of course, then there's no point of running this algorithm, but you just use a random policy. In fact, if you see the policy we started with, everything has 4 arrows. Every single cell had 4 arrows. Okay. So it doesn't really matter. Okay, this is the policy iteration algorithm. And I'll conclude, if I had timed it, I would have, I will conclude. By the way, the notebook I was looking for, it is actually here, the policy iteration grid world notebook. But due to memory issues, I could not remember. This is the original grid world problem that we have seen from the beginning of the previous lecture, right? So if you run the code and fully follow the code, this is going to be your pi star. For the specific parameterization again, if you change the rewards, change the gammas, change that, some others will change for sure. But for the specific parameterization, this is the optimal policy. So I will conclude with the value iteration. And the value iteration is, in fact, simpler. It does not necessarily need to go through this inner loop of evaluating the value function. It just basically the same says something, does a simplification. Go through just one sweep across the grid world and do the greedy on that. As it turns out, you don't need to go all the way into the actual value function, but you can actually stop in between. So it's like a strange kind of thing. I'm not sure if I have it here. Apparently, I don't have the thing. But if you go back to that previous diagram, the policy kind of iteration, come on. If you go back to the policy iteration, that is, it says you don't need to do this. You don't need to go and evaluate the policy, but you can actually take a shortcut and do hill climbing on whatever value one sweep will give you. Right? You don't have to iterate over multiple times. Remember the value evaluation, right? We have to iterate over multiple times for that v value vector, right? In order for it to converge. And the value iteration says you don't need to do that. Okay. You can imagine these arrows going in between, standing here, right, in some far away from the actual kind of value, coming back with greedy. Right? So this is actually called elements of what we will call generalized policy iteration. Yes.
So is it saying like you're only looking at the next state reward instead of like the state after that and state after that?
No, what you do. Remember, we had a system of linear equations, right? And you could actually say, okay, what would actually be the neighboring kind of states now, right? Go ahead and update those, right? And then do the greedy on those. And so you don't have to go into all exhaustively to come up with a proper evaluation. You're having a kind of, I would call it a noisy evaluation from the elements. Okay. That is the value function. Now, the same exact environment that I had for the policy iteration, I have now for the value iteration. Okay, so the value iteration code is actually here. So it looks at the Q values and estimates also the Q the Q values for the specific actions that are taken. So this basically is a Q star effectively that is being obtained. So you can actually go through all through this kind of code and sort of understand how the numerics kind of work. But in terms of value iteration, I think I have an explicit by hand. I have an explicit by hand example. Okay, step by step. Now I'm getting a little bit tired, honestly. I will close it. I'm sure, I mean, half of you are sleeping right now, but there are some of you are following, but most of you have sort of better things to do, I think, on a Friday evening. So what I want you to do at home, I will review this next time. Go 2-3 steps, the by hand evaluation of value iteration. And then go through also the Python code for both policy iteration and value iteration. We will use those algorithms as part of what's called generalized policy iteration to sort of start doing now reinforcement learning. In reinforcement learning, next week, we will stop having knowledge about the PSS prime. That will have significant implications to us because we need to now estimate value functions, not out of actual experiences, actual trajectories. We will not be able to expand in terms of the whole breadth of the tree and calculate the expectations. We have to create training data, and out of this kind of training data, out of actual trajectories, we have to estimate those value functions. And we will see if we manage to reach this kind of point, we'll see where we stop. The scope for the final exam, I will tell you next week what it will be. It may include reinforcement learning, but typically, because it's a last lecture and you have to deliver the projects and things like that, typically reinforcement learning may not be part of the scope of the final exam, okay, because it's the last lecture. Okay, so only MDP will be. Okay? That's the current working view, at least. Okay, but I'll tell you next week for sure. Yeah. All right, thank you. I need